Hello again, how are you? I see that you're saying a hi to me already, but go ahead and give me a hi, a hello, a what's up, a funny anecdote from your day, anything to let me know that you can hear me and you are ready to get started with today's acids and bases lesson. I know y'all were so excited because every single day when I said, do you know what tomorrow is? Somebody, at least somebody, and sometimes many of you were like, acids and bases. So I know you must be very, very excited. And I do want to take a moment. Yes. Oh, no, Adrian. I know. Listen. Didn't we talk about that yesterday? If this is something that you need to work on, you got to be here. That's the only way you can do it. Yeah, you know what I did? I crimped it. Is anybody old enough to know what that means? I know I'm showing my age right now, but I was like, you know what? Let me just bring back the early 90s right now. Let me just be a 90s girl. Thank you for pointing that out. I appreciate it. So yeah, it's acids and bases. I'm so excited to see you. And let me know too if anybody got an email from me today. Anybody got a coaching email? I feel like, oh, Hadil, I'm so excited because you were cramming and you cooked. Wait, but let me ask you this, Hadil. Do you still remember all of the facts, or are they already starting to run away? Because I bet you have signaled to your brain that you're done with that and it's running away. Oh, Peyton, good. And I will say, regarding emails, I'm pretty sure that right before this lesson started, I had got down to like 5 emails. Destiny, the emails, you did get an email, Peyton, I remember that one. I had got down to 5, just 5 emails right before I came to class. So if you didn't get your email, you're one of the unlucky 5. I'm so sorry, but I'm going to get to it first thing tomorrow. So you're almost there. Oh, look at that. See? Look at all those. It's been a lot of emails. So if I haven't got to you yet, don't worry. I'm going to be there. Okay, Hadil, well, we're going to do the countdown because we know from learning science, memory, retention, it's going to go away because you only needed it for that one day and you crammed it. You're so welcome, Crystal. You're so welcome. Let's get started. We're going to talk about our agenda. It's the same. It's the same as it was yesterday. So I'm not going to go over it too much. But we know we always start with a welcome and introduction. So welcome. We did it. Look how easy that was. Introduction. I am Coach Allie. As most of you know, if you're new tonight, then you don't know, but now you do. I am Coach Allie. And the reason I go by Allie, I like to say, is because my name is Carolina Turner. And when you have a name like Carolina Turner, you have to go by Allie. Otherwise, nobody can talk to you. So that is the story of why they call me Allie and why it's spelled all funny. But just Allie, very easy, like Alley Cat. And you can even call me Alley Cat if you want to. My mama does. So that's it. Welcome and introduction to me. Overview of the MCAT. We're going to go through this super quick because I'm pretty sure that y'all know by now, at least the general of the MCAT. Do we still have anybody who's new? Is anybody brand new tonight to studying for the MCAT? Like you just started today? Like this is your first day 1 MCAT study? Anybody? I didn't think so. I didn't think we were gonna have a lot tonight. We have the familiar crew is back together, which I'm really excited about. So really quickly, the MCAT is super long. Oh, Organic, welcome. Oh, we do have some newbies. Hi, Paya. All right, I'm not gonna rush through it then. And those of you who are not new, just hold on tight because apparently we do have a bunch of newbies. I didn't even know. Hi, noobs. Hello. Welcome to my class. I'm so excited to see you. First day. I always say any day can be the first day for MCAT. So I am very excited to see all of you. Well, we'll slow down a little bit. Let's start with this. The MCAT is really, really long. It's going to be a whole day affair. A whole day. Once you have your breaks, it's a whole day affair. And it's owing to this. There are many, many questions in each section. And even though it's a whole day and that's like a lot of time, those of you who've been studying for a little while, who've taken your practice test, why don't you go ahead and tell our newbies, does it ever feel like you really have enough time? Do you ever feel like you have enough time? We've talked a lot about timing this week. We've talked about how to get more confident, how to learn to ignore the timer, how to make more efficient use of the time that you have. But it will always be a constant thought on all of our minds, I think, as we continue to prep for the MCAT, or as you continue to prep for the MCAT, because I don't have to do that anymore. Sorry about it. So the test is really long. Here you go with your scoring. If anybody's familiar with the scoring of the old MCAT, they really haven't done that much. They just moved it right up the number scale. You will have a separate score for each section, and your combined score out of all of those is going to make out your total. Some of you emailed me and asked me about the curve of the MCAT. And I saw that we had like a little bit of misconception. You're not curved against other students. The tests are they're scaled. So they are essentially curved against other tests because they use different questions every time. So sometimes they'll say, okay, they try and make it the same level of difficulty, but sometimes they'll be like, okay, I think this one is a little bit more difficult. This one is a little less difficult. And so that's what it is that they're just kind of scaling it. So that if you get a test that's like a little bit harder, they're a little bit easier on the grading of it. Or if you get a test that's a little bit easier, they might be a little harder on the grading of it, but it's nothing to worry about. It's so slight. It's so slight. So no worries about that. This is your science content on the MCAT. Y'all know that I feel like y'all think I'm on a war against content. I'm not. You got to know your content. This is a logic test. It's not a science test. It's a logic test, but they do speak the language of science. So you got to get your content up. But you guys know, I say it all the time, it's your foundation. It's your foundation. So we've talked a lot, and I had a lot of emails about how to use the 7 series books and what they're great for and what they're not going to do for you on the way to MCAT success. And what they're great for is building up your content. I don't think that you need to read every single page of every single chapter. That's very rare that a student would need that. So you have to highlight exactly what you need and go for it. Here at Kaplan, we do science content tests to make sure that our students are taking the right chapters, doing the right videos, going to the right lessons. But you at home, what you can do is kind of assess your own skills, maybe by taking a practice test and seeing what you got wrong. We've talked this week already about always making a why you got it wrong sheet and be very honest with yourself. And sometimes it can be a couple things. I was rushing. I didn't answer the right question. Also, I didn't know the content. So it can be several things. But if you see consistently a pattern in the content and the type of content that you're missing, that's something to target in your 7 series books. And outside of that, your 7 series books, I want you to target the highest yield. Not all chapters are as high yield, and we knocked something over. We have it all marked. So look for those high yield concepts and make sure to prioritize those and spend more time on them. MCAT skills. MCAT skills. This is my favorite slide. This is my favorite slide that I get to go through. And that's because it really shows the point that I'm trying to make here, which is that your science is just check number 1 on your way to MCAT success. You need a whole lot of other things to be put there. And we've learned a lot about them this week. And I know we got some newbies. So those of you who have been with me this week, can you just shout out one thing or even multiple things that you've learned this week that are outside of content but will absolutely help you on the MCAT? What else have we learned about this week? Because you know you're going to make a teacher's day come true if you just give me one thing, just anything that you learned. I know yesterday I put the poll up and one of my very favorite things came up in the word cloud, like super large. So I know that you guys have been paying attention and that makes me really, really happy. And that word was patterns. It was looking for patterns. It was looking for things that can help you. You guys also felt like, oh, Simona, you were the first one to say it. Jillian, strategy, I love it. Sydney, dump the hunk. We're always going to remember that, right? Elimination, of course. Sometimes you can eliminate all the way to the right answer. Easy questions first. Thank you. Make efficient use of your time. Chunking. Oh, I love that. Different techniques and styles in your study. That's awesome, Peyton. That is what we learned in yesterday's coaching session. And that came right from memory and learning. That's a psych-soc topic, and it applies to you now because you need your memory and you are learning. Oh, patterns, patterns, patterns. Conceptuality. Sawyer, getting all fancy with me. I love it. Chunking. Yeah, we're going to take it in chunks. We're going to take little pieces of it because sometimes you look at the whole question and they've made it so convoluted and they throw in those red herrings, those words. They're like the kidney or the tumor. And all of a sudden you think you got to be an oncologist or a nephrologist. You don't. Chunk it. Look at it. There's small bits of science. And if you use the small bits of science that you know and then put it together, voila. So I'm glad you have made a teacher's day. You are starting to see all of the different things that you're going to need to put into play on the MCAT. And I can't tell you how very happy that makes me as your Kaplan Plus coach for the week. But now it's time for me to give you away. Today's teacher is amazing. He's actually so amazing that I have never worked with him before today because they never deigned to allow me to meet him. He's very, very good. His name is Tyler. You are going to love him. I've watched his lessons, but I never got to be like in person with him until today. So I'm super excited. I'm going to finally get to watch Tyler live. So this is a big, huge deal for me as well as you. And I'm going to hand you over now. Tyler, go ahead and come on screen. Take your class over. They're amazing. They're awesome. They're ready to go. And they're super excited about acids and bases. Y'all, I will see you later. Bye-bye.
Hey, everybody out there in MCAT land. That was quite an introduction. I'm not sure I've ever been talked up quite that much, but how are you guys doing out there in the world of MCAT tonight? Excited to be here, I hope. Pumped, because I know I am excited to be here. Rock on. Yeah, cool. Hey, guys. Hey, Shivalik. Adil, what's going on? Nice. Hey, let me ask you guys this question, because this is my favorite part about teaching online. You guys, has anybody taught you the thumbs up, thumbs down? 6 for thumbs up, 9 for thumbs down. You guys tell me, thumbs up or thumbs down. How many of you guys out there are wearing sweatpants or basketball shorts right now? Give me a thumbs up, thumbs down. Hey, Simona. The secret, my secret, me too. Yeah, here we all are in our sweatpants about to learn some acids and bases. So this is, I think, it's a really good privilege to teach you guys all in this online environment. A few actual pants out there, a few actual pants wearers out there, but mostly sweatpants. I don't know, it's kind of cool. We get to, you guys are probably on your couch, or, your dining room table. Hopefully not in bed, right? Don't study where you sleep. But what we're going to learn about tonight is one of my favorite topics. I was actually a chem major, so I'm kind of a weirdo. We're going to talk about one of my favorite subjects, which is acid-base chemistry. There we go. And we've got a lot to cover tonight. We're going to cover kind of the basics about acids and bases. And if you guys look at our agenda, kind of our learning objectives for the evening, what we're going to be studying first and foremost is acid-base strength. And then we're going to be turning to one of the hardest topics, in my opinion, calculating gram equivalent weight and normality. Our first objective is to determine acid and base strength. And really, before we get into acid-base strength in general, I want to talk to you guys about kind of the history of acids and bases. Because if you guys remember acid-base chemistry, there's these 3 different definitions, right? The Arrhenius definition, and then Bronsted and Lowry came along and redefined acids and bases. And then there's the Lewis definition, a little bit later on as well. And I always thought, why don't they just pick the best one and stick with that? And that's kind of what we're going to do tonight. The MCAT focuses primarily on the Bronsted-Lowry definition. And I'll talk to you guys about why it's so important as we go. But I want to start off with what even that is, right? So 1923, these 2 scientists, Bronsted and Lowry, actually totally independently, they didn't even know each other. They both happened to come up with this idea the same exact year. They said an acid is a special kind of molecule that is going to dissociate to give me what? What does an acid break apart into? What makes an acid, I guess, according to Bronsted and Lowry. Bronsted, Lowry, they said acids are, proton donors. These guys split apart in solution to give me H pluses, protons, right? That's pretty cool. Actually, that wasn't new news. My buddy Svante Arrhenius back in 1883 won the Nobel Prize for defining acids as proton donors. So this was not actually new news at the time, but what was new news, what was a really big deal, according to Bronsted and Lowry, what is a base? According to Bronsted and Lowry, what is a base? Oh, see, and Adil, this was actually the big revolution, is that up until Bronsted and Lowry, people thought OH minus was a base, right? That was, again, Arrhenius back in 1883, more than 100 years ago. He said OH minuses are bases. But let me actually point out something really cool, right? Think about this. OH minus is a proton acceptor. So Bronsted and Lowry came along and they totally changed everything in 1923. They said that a base is a proton acceptor. And this is for Adil. Remember, OH minus is a great proton acceptor, right? So when you guys think OH and you think base, there's a very good reason for that. It is also a proton acceptor. So this maybe doesn't sound like it's going to change the world. It totally does change the world. It opens up chemistry. It unlocks brand new branches of chemistry. It has huge consequences for organic chemistry and biochemistry. If you ever wondered why acid-base chemistry is so important, that's a big part of it right there. It just is, it's part of so many things, right? Amino acids, fatty acids, nucleic acids, all really important as proton acceptors and proton donors. But what this really means, the really important part about this is, let's imagine that I am an acid, right? Let's imagine that I'm some kind of, usually we're going to use this terminology today a lot, so we'll go ahead and use it right now. Scientists will often write H, there's my proton, and then some other bit of molecule, right? They call it A, short for acid, or the other part of the molecule. But I go ahead and act like an acid. I give up my proton. I donate my proton. And what I'm left with is just the leftover bit of molecule, which notice has this negative charge. So after I give up a proton, now I'm negatively charged. What kind of molecule am I now that I have given up my proton? What kind of molecule do I become after I give up my proton? Yeah, I become a base, right? So what Bronsted and Lowry's big contribution was, right? They kind of stopped thinking about this molecule is an acid and that molecule over there is a base. And they just said, look, there is the protonated form of a molecule, right? There is the acidic form of the molecule. And then there is the deprotonated form of the molecule, or there is the basic form of a molecule. They stopped thinking about it in terms of acids and bases. You are this, you are that. And they start looking at it as a molecule either has a proton or it has lost its proton. And guess what? If I've lost my proton, maybe I want it back. Under certain circumstances, that same molecule that gave up a proton just a minute ago is going to try to get that proton back pretty soon, right? So they stopped thinking about it in terms of acids and bases, and they started thinking about it in terms of the protonated version and the deprotonated version, or the conjugate acid and the conjugate base. It's kind of the same molecule, just with or without a proton. The other thing that Bronsted and Lowry did was they introduced the notion of strong acids, strong bases, and weak acids and weak bases. And I want to talk about this because this is one of the most, I'd say, often misunderstood or even really hard to understand topics in acid-base chemistry, on the MCAT period, frankly, and that is, what makes an acid or base strong or weak? What is the relationship between strong and weak acids? And let me ask you guys, this is a good starting point, right? Usually when I ask students, what makes a strong acid? You guys tell me, in your own words, what makes an acid strong? How do you recognize a strong acid? How do we recognize strong acid? Yeah, usually that's what I hear is strong acids are those that completely dissociate. Completely dissociate. Yeah, and absolutely, we're going to be looking at the conjugates of their bases, or the strength of the conjugate base as well, right? So this is actually what I want to drive at. I want to get into this world of strong acids, strong bases, weak acids, weak bases, and kind of sort out all, because you guys give me a lot of great ideas, right? Is it how readily they donate protons? Is it their stability? Does it have to do with the strength of the conjugate base? There's all of these ideas kind of swirling around, and I want to get to the heart of it. I want to nail this to the ground so that you guys have it with you on test day, right? We usually think about strong acids as those that completely dissociate in solution. And a good example might be like HCl, right? If I take some HCl and I throw it into solution and I come back 5 minutes later, I don't expect to find any HCl's in solution. I expect to find H's and I expect to find Cl's. I expect that they will have split apart completely. So then we want to think about the other side of the coin, like a weak acid, right? If that's what a strong acid is, let's think about what a weak acid is. And again, let me ask you guys, if a strong acid, if we're going to say a strong acid is one that completely dissociates in solution, how might we define a weak acid? Strong acid, we're saying completely dissociates. How might we define a weak acid? Cool. Yeah, we could think about it as incomplete dissociation, right? Very little dissociation. Exactly, Raghav. Yeah, partial dissociation. Exactly. Yeah, Organ May. Exactly right, Lenora. Yeah, incomplete dissociation. Let me give you guys a great example of a weak acid, hydrogen fluoride. And I love the example of hydrogen fluoride because I want to talk to you guys about what a weak acid is not, right? You hear weak acid, and I think one of the reasons why this can be so confusing is that in the English language, the word weak already had a meaning before chemists came along and applied it to acid-base chemistry, right? So it's easy to think weak acid must be something that is like not very potent, not very powerful, maybe that it's safe to play with. I could, I don't know, stick my hand in it or something like that. I don't know why you'd want to do that. But then you come across the example of hydrogen fluoride. Hydrogen fluoride is a weak acid, and you guys might recognize hydrogen fluoride from the television show Breaking Bad, right? Anybody a fan out there of Breaking Bad? You guys tell me, what do they use hydrogen fluoride for in the TV show Breaking Bad? You guys recall? It's not to make drugs, actually. Yeah, it's kind of a gross analogy, I guess, but they use hydrogen fluoride to dissolve people, right? To dispose of dead bodies, which is, again, it's sort of a morbid analogy, but it sticks with you for that reason. Hydrogen fluoride is a weak acid, but it is not a safe acid. It is not a non-dangerous acid. It is not an impotent acid. It's not an unreactive acid. It is a weak acid. And for our purposes, weak means incomplete dissociation. It can still be very dangerous. It can still be very reactive. It can still be something that you want to be very careful around, even if it's a weak acid. Because again, in chemistry, weak acid means something very specific. It means incomplete dissociation. Now, let me ask you guys one more question about this, right? If you take a look at my chemical reaction, how can you tell at a glance by inspecting just this chemical reaction here that I have incomplete dissociation and therefore that this is a weak acid? What is the telltale sign that tells me that this is going to be a weak acid? Yeah, surely. Arrows. Yeah, the equilibrium arrows. When we think incomplete dissociation, we're going to be thinking about equilibrium. This, ladies and gentlemen, is why acid-base chemistry, especially Bronsted-Lowry acid-base chemistry, is so important for the MCAT. Acid-base chemistry, pretty cool, pretty important, right? Equilibrium chemistry, that is one of the most important topics on this test because it just shows up everywhere. For example, almost all reactions are equilibrium reactions. Certainly almost all of the biochemical reactions in your body are equilibrium reactions. When we think about the dissociation of amino acids or fatty acids in the context of biochemistry, that's all about shifting balances of equilibrium. And so this is the big tie-in. This is what elevates acid-base chemistry to super high yield on the MCAT, right? And anytime we talk equilibrium, we can't get too far without talking about the equilibrium constant. Notice in chemistry and acid-base chemistry, this takes on a special name, the acid dissociation constant. But it's just a good old-fashioned equilibrium constant. KEQ is KEQ is KEQ, no matter what you call it. So let me ask you guys, in your own words, what does the equilibrium constant tell us? How might we qualitatively or loosely define the equilibrium constant? How might we loosely define the equilibrium constant? Nice. Yeah. When I think equilibrium constant, I think about the ratio of products divided by reactants. And exactly right, right? This tells us about the balance of products and about the balance of products and reactants at equilibrium. There we go. Products divided by reactants. And that is exactly true for acids and bases as well. Products over reactants. Yeah. And so I love it. Like Sawyer says, for an acid specifically, notice that my product, in this case, is a proton, right? What makes an acid is that it's a proton donor. And so if I have a relatively large equilibrium constant even, what we're going to see is that this shifts over towards more protons. And so the bigger the equilibrium constant, the bigger the Ka, the more reactive an acid is, and the more it is going to give us those products. So let's come back to what makes an acid or base strong versus weak, right? Weak acids we know are equilibrium. Strong acids, we said for now, are complete dissociation. What would you guys predict about the K value, the equilibrium constant for a strong acid? If I'm a strong acid, if I'm nearly completely dissociating, if I am almost all products after you throw me into solution, what would you predict about the value of that Ka? Yeah, we're going to be almost all products, right? A very large K value. Nice job, everybody. Nice job. Now, and you know, a couple of you guys got that exactly wrong. You got that exactly reversed, right? That is fine. I totally love wrong answers. I'll tell you guys, they are one of my favorite things ever. Because wrong answers in here, right now, on this very moment, equal right answers out there on the real test, right? It's a simple equality as long as you learn from your mistakes. You know, the worst thing that's ever going to happen while we're meeting together if you miss a question is, I'm going to know, oh, we better talk about that a little bit more and get to the bottom of this. And Melenis, yeah, the whole Ka pKa thing is really easy to get backwards. I'll guarantee you guys, I have missed more questions in acid-base chemistry because of making that mistake than probably all of you guys combined. I've been doing this for a long time. Everybody makes mistakes. But yeah, the point is, if we're thinking about the K value for a strong acid, they say it's going to be high. You know, actually, there is an official definition of strong acids. It's not that they have a big Ka. It's not that they completely dissociate or approximately completely dissociate. It's not even that they favor products. The official, like, chemistry teacher sanctioned definition of a strong acid, they have a Ka greater than 1. They have a Ka greater than 1. That, to me, feels so much more satisfying than this whole, like, strong acids nearly completely dissociate. Like, unicorns are pretty and clouds are fluffy. And strong acids nearly dissociate in solution, right? Nearly completely. Rather than speaking loosely and sort of in metaphors and analogies, we can say very rigidly, strong acids have a Ka greater than 1. Weak acids have a Ka less than 1. In fact, let me write that down. Weak acids have a Ka less than 1. That is a very rigid definition, and that feels very satisfying to me. So let's move on, right? If this is both acids and bases, I want to talk to you guys about bases as well. It turns out that all of this same conversation applies to bases too. A strong base, we could say loosely, completely reacts or nearly completely reacts in solution. A weak base is one that is all about equilibrium chemistry. Or we could say very explicitly, the base dissociation constant, KEQ for a base, not if is high for a strong base, but is greater than 1. And similarly, for a weak base, we would be talking about a KB that is less than 1, right? Very rigid. Very, very concrete definition. We're going to get a little bit into the numbers tonight, so it's good for us to have some touchstones, right? All right, let's talk about some common examples of strong acids. You guys, give me an example. Give me your favorite common strong acid. And I already told you, HF, not a strong acid, right? That's really easy to get mixed up on, and we'll see why in a second. But what are some examples of acids that are strong acids? Yeah, I'm glad that HCl comes in first, right? HCl is like the MCAT's quintessential strong acid. If you see HCl, you should be thinking strong acid-based chemistry. But then, and I love it, it's, is it Navjot? I'm sure I didn't say that right. I apologize. But going right on down the line, right? HBr, HI, literally our first 3 answers just go down the period of the periodic table. The odd man out is HF, right? The only hydrogen halide that is weak is HF, but all the other ones, HCl, HI, HBr, all of those guys are going to be strong. And then just the names of some of the other ones, sulfuric acid, nitric acid, chloric acid, perchloric acid, these just sound nasty. In fact, let me give you guys the whole list here. You can check your answer against this list, right? There are 7 on this list. 7 of them for us to know. That sounds like maybe a flashcard or a set of flashcards, right? But there's actually a really good reason to memorize and to learn and to know these 7 strong acids, because on test day, if I see any other proton donor, what kind of an acid is it if it's not one of these 7? Any other proton donor has got to be a weak acid. Yeah, if you see an acid that's not one of these, if an acid is not one of these, it must be weak. Must be weak. You guys got it, right? So let's learn the 7 strong so that we know all the others that are weak, right? And when we think weak, we think Ka, we think equilibrium, incomplete dissociation. All that stuff is fair game the minute that you see a weak acid. As far as strong bases are concerned, it's not quite as cut and dried. First of all, if I have a hydroxide salt of any group 1 metal, then that is going to be a strong base. Let me say that again because I messed it up. If I have a hydroxide salt of any group 1 metal, it's going to be a strong base. So sodium hydroxide, potassium hydroxide, cesium hydroxide, right? You guys know that somebody like sodium is going to be super stable in solution. Same thing for potassium. So somebody like sodium hydroxide is just going to split apart, just like sodium chloride, like table salt splits apart in solution. All of the group 1 metals are going to make for strong bases. There are a few others that are strong bases as well. One that we'll tonight, and we'll talk a little bit more about him when his turn comes. But NH2 minus, you guys might recognize NH3, who we'll see tonight as well, but NH2 minus, sort of the big brother of ammonia, that's a strong base as well. Also one that pops up in surprising places, hydride. So not a proton, not a normal hydrogen ion, that is not a normal, not a normal hydrogen atom. A lot of vowels in there. But hydride, the anion version of hydrogen, also is a strong base. He's just this really reactive little dude who's got too many electrons in too small of an area, and he's going to go around attacking other molecules to try to give that electron away, binding up with another proton maybe to form H2 gas. Those are probably the most common strong bases that you'll see on the MCAT, but because it's not so cut and dried, it's usually the acids that they focus on rather than the bases. So with that, and again, we've kind of foreshadowed where I want to go next. What I want to do next is dive into some numbers and some math with you guys. This is really important for the MCAT, but don't worry, I am not going to beat a bunch of math over your head. What we're really wondering about here is building a qualitative kind of understanding about what Ka means, what relative Ka values can tell us, and really, frankly, where Ka and Kb even come from. So our first example is acetic acid. Let me ask you guys, do you know in my everyday life, where do I find acetic acid? This is just a fun fact. It's probably not going to be on the MCAT, although they could reference it, but they wouldn't necessarily need you to have it. Where do we find acetic acid? I almost gave it away just now. Where do we find acetic acid in our everyday lives? Vinegar. Yeah, it's delicious. I put it on everything. I put vinegar on my French fries. I'm sure some of you East Coast people do that as well. If you're thinking that sounds gross, keep in mind that ketchup is mostly vinegar. So you're putting vinegar on your French fries as well, right? This is delicious. We eat it, we put it in our mouths, we chew it up, we swallow it. Clearly, this is a weak acid, right? But I want you guys to keep in mind, weak acids, they are not necessarily safe. This one just happens to be one of the less potent, less reactive ones, one of the more mild or more safe ones. So let me ask you guys, right off the bat, if we were going to start thinking about the value of this guy's Ka, acetic acid, pretty unreactive, right? It's not dissolving anybody's body. We put it on our French fries. What would that imply about the value of Ka for this particular acid? Pretty low. Yeah, exactly, Jeremiah. Pretty small. Much, much less than 1. Right? And in fact, if we look at the actual value, you do not need to memorize the value for test day, but we do need to understand what this value means. Ka, 10 to the minus 5, so this is 0.000001. Yeah, that's a pretty small number. That tells me this guy is pretty unreactive. Let's go ahead and put it on our fries. And that's a really good question. It absolutely is necessary that we balance these reactions in order for us to make sure that we get the dissociation constants correct. But gang, there's actually a really good piece of good news. A good piece of good news here. For acid dissociation reactions, it's always going to be exactly the same. You're going to have the acid, and it's going to split apart into a proton and the deprotonated form of the acid. And that's actually exactly what we're seeing here, right? We've got an acid. It gives its proton to water. And what's left is the deprotonated form, the conjugate base, if you will, of this acid, right? So these are really easy to balance. It's kind of nice. Almost always on the MCAT, by the way, these will be balanced. Acid-base reactions, because there's not really any tricks the MCAT can throw at you, generally are going to be balanced. So then we take a look at somebody like HCl, and again, we know that HCl is going to be a super high reactive acid. It's a strong acid, so its Ka is going to be greater than 1. Notice the Ka for this guy is about 10 billion, right? It's not just a little bigger than 1. It's way, 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 way bigger than 1. The math works out to about 999 out of every 1,000 HCl molecules end up splitting in solution. So we can say approximately, nearly, this reacts to its completion, right? But this is what we're looking at with a strong versus a weak acid. The strong versus a weak acid. What I want to talk to you guys about next is another observation that Bronsted and Lowry came up with that has to do with the autoionization of water reaction. And this will tie back into acid strength. But when we think about the word autoionization, let me ask you guys, what does the prefix auto mean? We actually see this come up a lot in bio. I think about cells that self-destruct, that has the prefix auto as well. When we think auto, what does it mean? Allie got me with that last joke. Yeah, self, right? water is going to self-ionize. It's going to self-split apart. We're going to have a molecule of water that reacts with another molecule of water to form a H3O plus and an OH minus, right? The very definition of acid and base we get right there in water. Now, let me ask you guys a couple of questions. Just, again, our goal here is not the numbers. It's to think about qualitatively what they mean. How likely is it that super stable, pretty inert, really happy water is going to automatically react with itself to give me the definition of a strong acid, H3O plus, and the definition of a strong base, OH minus? How likely is it that we're going to see this auto reaction happening? Yeah. Not bloody likely, right? Sorry, that was a terrible accent. Not very likely at all. Very, very low, right? And we see that reflected in the equilibrium constant for this reaction as well, right? This one, like all equilibrium reactions, and actually let me be clear, this should be not a one-way arrow, but an equilibrium arrow. Like all equilibrium reactions, this is going to have an equilibrium constant. And notice this equilibrium constant, I mean, it's practically zero. It's like infinitesimal, 10 to the minus 14. That's a decimal place with 13 zeros and then the number 1 after all of those, right? So we see that this is not very likely. We would predict it's not very likely, and the math backs that up. But there's actually there's a really important observation in here. If we take a look at this, notice that and again, let me write this out a little bit more so you guys can see this a little bit more clearly. We don't have two H2Os. We have an H2O and his buddy H2O. And what I want you all to notice is that in this reaction between these two water molecules, one of them gives a proton to the other, right? My guy here on the right pops over a proton onto my guy here on the far left. Now, my question for you guys, any molecule that donates a proton, any molecule that donates a proton, what do we call that molecule? Yeah. Proton donors are bases, right? Proton donors are acids. I'm getting ahead of myself. Proton donors are acids. You guys are exactly right. Thank you. Everybody makes mistakes, right? Wrong answers in here make for right answers later on. Proton donors are acids. Any molecule that donates a proton is an acid. So what we see here is water acting like an acid. And notice my buddy, the guy that I wrote in green there, he is acting like a base. In this autoionization reaction, we see water itself behaving as both an acid and a base. And so what we see with this Kw value, not only does this tell me how likely water is to autoionize, right? Answer, not very likely. It also tells me how reactive water is as an acid or as a base, right? It kind of gives us a benchmark. Another really important number, right? Like if the defining point of a strong acid is Ka equals 1 or greater, this gives us another really important number to consider. Kw, how likely is water to react as an acid or base? But we're not quite done there. The hits just keep coming in, right? Because what Bronsted and Lowry did, something I think is really, really brilliant. They took a look at any weak acid. We've got acetic acid here, but they took a look at acetic acid. They said, okay, we know the Ka for acetic acid. Maybe we measured it or calculated it. And then they took a look at the conjugate base of acetic acid, right? They said, let's look at how acetate, the deprotonated version, behaves with water. And notice that the conjugate acid turns into the base and vice versa in both of these two reactions. But what Bronsted and Lowry did, their really brilliant observation, getting ahead of myself here, is they said, let's treat this almost like a chemical mechanism. Let's pretend this was like a two-step chemical reaction, and let's sum up these two sides. And my question for you guys is this. If I have a chemical mechanism, a two-step chemical mechanism, and I notice that a molecule is the reactant in one step of that mechanism and the product in another step of that mechanism, what happens to those molecules when I try to find the net overall reaction? Sorry, Ariel. I just saw your comment about my earlier mistake. Yeah, if I've got something that is the reactant on one side and the product on another side, Ollie, exactly, they're going to cancel out. So we go ahead and cancel these guys out. And we add up the rest. And let me ask you guys, when I do this canceling and add up the rest, what am I left with? What is the result of this set of steps? Let's see here. After I do my canceling on the left, I've got water. And on the right, I've got myself an H3O plus and an OH minus. Yeah, so what's left? The net reaction. Raghav, you got it, dude. Yeah, what we're left, Jillian, dude, exactly. Salam, nailing it. What we're left with is exactly the water autoionization reaction. Why this is important is it had been previously demonstrated is if I have a multi-step reaction and each step has its own individual K value, and I have the net reaction, which has its overall K value, the steps are related to the overall K value by this reaction, by this equation that we're seeing here on screen. This gives us a relationship between the K value of a weak acid and the K value of its conjugate weak base. In fact, I'm going to try not to make you guys do too much math tonight, but this one is so important, and it's such a good opportunity for you guys to flex your scientific notation skills here. I want for you guys, we know the Ka of acetic acid, right? 10 to the minus 5. We know the Kw value, the overall water ionization value. So will you guys please solve for me and find Kb, the equilibrium constant for acetate, the conjugate base? If we go through and solve for Kb, what do we get? I'll start working it on screen as well. 10 to the minus 14 divided by 10 to the minus 5. Yeah, right? So when we divide, we subtract the exponent. Minus 14 minus negative 5 is going to give me 10. To the minus 9. Good deal. Right on, everybody. Let me get rid of some of my chicken scratches so I can write this in here. 10 to the minus 9. Now let me ask you guys, if we're thinking about acetate, right? Acetate, this CH3COO minus, the conjugate base of acetic acid, its K value is 10 to the minus 9. What does that tell me about the strength of acetic acid? It's less than 1. So is it strong or is it weak? Yeah. So keep in mind, strong bases are greater than 1. Yeah, this has got to be a weak base. And what we see on this, what we see in this overall is when we think about any acid, any weak acid, right? Any weak acid like our acetic acid here, we know that weak acid means actually equilibrium. So instead of this one-way arrow, I'm going to replace that with an equilibrium arrow. What that guy is in equilibrium with, what that weak acid is in equilibrium with, is his conjugate base, right? Now, if equilibrium means weak, what we see here is that the weak acid and the weak base are in equilibrium with each other, right? They're both in the same equilibrium. Equilibrium means weak. This is, in my mind, one of the easiest things to screw up in all of acid-base chemistry. The conjugate of a weak acid is always a weak base. I'll say it again. The conjugate of a weak acid is always going to be a weak base, right? If we look at the conjugate there, we see that they're both less than 1. And so they're this guy and this guy are both less than 1. And so this has to be a weak base. But let's turn our attention now to a strong acid, right? Let's think about what this math would work out for a strong. And again, I'm not going to ask you guys to do a lot of math today, but let's use that same equation. We had Ka times Kb equals Kw. If you guys go ahead and plug into this equation for my strong acid, for HCl, tell me what you're going to find for the Kb of chloride. Equals Kw, which is 10 to the minus 14th. When we solve for Kb, what are we going to get for that deprotonated version, for that conjugate? Yeah, if we solve for Kb here, what we find is that in this case, the Kb is 10 to the minus 22. 10 to the minus 22. So then watch out for your minus signs. And I'll write this out really quick. We're going to divide both sides by Ka, so we're going to divide by 10 to the now positive 8th. Right, 10 to the minus 14 divided by 10 to the positive 8 is going to be 10 to the minus 22. 10 to the minus 22. So let me tie all this together, ladies and gentlemen. Right, this is the ultimate point that we've been driving at. From the water reaction, we said that the Kw of water tells me about how basic water is, right? How likely it is to accept a proton, and we know that the Kw for water is 10 to the minus 14. What this number tells us about chloride is that chloride is 100 billion times less likely to accept a proton than water is, right? It's 100 billion times less basic than water. Let me ask you guys one more question on this. If a molecule is considered to be 100 billion times less basic than water, can we really even call it a base at all? If a molecule is 100 billion times less basic than water, can we really even call it a base at all? No. Probably not. Samuel, sodium. You got it, dude. No. Probably not. So this is the point that I want to make with you guys. When we think about the whole spectrum of acids and bases, if we think about an acid, for example, there are a couple of important numbers that we want to keep in mind, right? Ka equals 1. If my Ka is greater than 1, by definition, that is a strong acid overall. The other number that we want to keep in mind is 10 to the minus 14. Remember, that's the reactivity of water. So if we think about a molecule whose K value is less than 10 to the minus 14, that means that molecule is actually less reactive than water. It's less acidic than water overall. In other words, it's basically inert as a molecule. And it's in this middle range, from 10 to the minus 14 up to 1, that we get our weak acids. Anybody in that middle zone is a weak acid. This is, I think, a really important observation, right? Because it means that there's actually 3 ways that we could categorize a molecule. And it makes perfect sense, right? An acid is it's a strong acid, a molecule is a weak acid, or some molecules just aren't even acids at all, right? Similarly for a base, right? A molecule is either a strong base, a weak base, or it just isn't even actually a base at all, right? Not every molecule has to be an acid or a base. So what I want to do now that we've kind of set these definitions in order, let's take a look at the comparison of acids and their conjugate bases, right? Let's think about the different kinds of numbers that we might see here. And I'm not going to ask you guys to do any math, but we're going to show a lot of math on this screen. What we saw for HCl, the K value for HCl was 10 to the 8th. So we know it's a strong acid because its K value is greater than 1. If we take a look at its conjugate, right, its deprotonated version, this guy over here is going to be 10 to the minus 22. That's what we saw just now. So it's not even actually a base at all. Chloride is generally considered to be inert and unreactive in solution. Take a look at H2SO4. Let's go down our chart here. You guys tell me, what kind of an acid is H2SO4, sulfuric acid? What kind of an acid is H2SO4? Yeah, this is a strong one. Absolutely, this is a strong acid, which means its Ka is greater than 1, which means that if we deprotonate it, the conjugate of that, the deprotonated version, is again inert as a base. HSO4 minus isn't even actually a base as well. Similarly, nitric acid, HNO3, is a strong acid. When I deprotonate it, I get nitrate. One of the things to know about nitrate is that it is a super stable, super happy, super inert ion. Just kind of hangs out. That's important for solubility rules as well. When I have salts of a metal with nitrate, they're almost always soluble because nitrate's like, cool, bro, you know, I'll hang out by myself. And if I bind nitrate onto a proton, the same thing happens, right? Nitrate's like, all right, proton, you're free. Go do your thing. And I'll just hang out by myself because I am inert, right? Not even a bit, not a weak base, not even a base at all. So then let's start getting into some of the weak bases, right? And again, you guys have done enough math for me tonight. So if we take a look at this first one, 10 to the minus 2, right? This is a pretty reactive weak acid. This is one that you do not want to stick your fingers in Chem Lab because even though it's a weak acid, that relatively large Ka tells me it's going to be pretty reactive. And then I take a look at the Kb for that. When I deprotonate it, 10 to the minus 12. Let's keep going with the trend, right? Phosphoric acid, H3PO4, is 10 times weaker. And notice the number for the base, hydrofluoric acid. Okay. So let me actually stop here and ask you guys for a trend, right? As my Kas get smaller and smaller and smaller, what effect is that having on the Kbs of the conjugate? If we take a look in the fourth column, as the Kas get smaller and smaller and smaller, what effect does that have on the Kbs in that other column? And Joey, you're exactly right. I just saw your question. Are we saying the conjugate base of a strong acid is essentially inert? That is correct. Yeah. And if we look at our weak acids, notice as my weak acids get less and less reactive, their conjugates are getting more and more reactive, right? We're seeing the exact opposite trend. This is actually part of the equation Ka times Kb equals a constant Kw, right? What this is saying is, again, by the mathematics, as the Ka is getting smaller and smaller, the Kbs have to get bigger and bigger. But what I want you guys to notice, and this is really important, all of my acids are weak. All of my conjugates are weak as well. All of these guys fall in that magic range of somewhere between 1 and 10 to the minus 14. But there's a relationship within that range. The more reactive my weak acid, the less reactive its conjugate weak base will be, and vice versa, right? The more reactive a conjugate weak base, the less reactive the conjugate weak acid. And it makes total sense, right? If I'm an acid who's pretty ready to give up my proton and act like an acid, I'm not going to be super excited to get that proton back, right? I'm like, hey, I gave that away for a reason. So we see that this relationship exists. And in fact, if we keep going right on down the chart, you'll see that this trend keeps on continuing. Acetic acid, we saw already, right? This guy is vinegar. He is slightly less reactive, and his conjugate base, acetate, gets slightly more reactive. We think about ammonium cation, right? Ammonium cation is kind of almost barely an acid at all. And the conjugate of it, ammonia, is a really pretty run-of-the-mill, middle-of-the-road weak base. In fact, ammonia is one of the MCAT's favorite weak bases. If you ever see ammonia, you might want to start thinking the MCAT's probably trying to give me a hint that this is a weak base. Hydrogen cyanide, again, almost not even an acid at all, just barely more reactive than water. Its conjugate cyanide, actually a pretty powerful weak base, right? I think we all know you don't want to be messing around with cyanide. You can sort of see why here. It's a pretty reactive base. But now let's take a look at NH2 minus. Let me ask you guys, what kind of a base is NH2 minus? Right, Ali? Patterns on the MCAT, who knew? What kind of a base is NH2 minus? This is one we called out earlier. If you're not sure, the data is right there on the screen, right? Yeah, it's a strong base. It's a strong base. We can see that because the Kb value is considered very large, aka greater than 1. And let me point out, guys and gals out there, NH2 minus is such a strong base that when I give it a proton to form the conjugate, I get ammonia. Ammonia, we know, is also a base, right? That's how strong a base NH2 minus is. When you give it a proton, it still wants more protons, right? It's still a freaking base. So that's what we're seeing here, right? The conjugate acid, so to speak, the protonated version of NH2 minus is not a weak acid. It's not even an acid at all. When we protonate NH2 minus, we get a molecule that is still a base. Similarly, if you take a look, I mentioned the hydride anion a little bit ago, right? That's a really strong base, and when I protonate it, I don't get an acid per se. I don't get a molecule that reacts like an acid. I get good old-fashioned, relatively inert hydrogen, right? Hydrogen is, at least in terms of acid-base chemistry, inert. You certainly don't want to hold it near a flame. It will combust, but it will not split apart into protons and proton acceptors, right? So again, the big takeaway, and I want you guys maybe write this down. This is such an important point. The conjugate of a weak acid is a weak base. Always. Always. They're pairs. They're in equilibrium with each other, right? The conjugate of a strong acid is inert as a base. And the conjugate of a strong base is inert as an acid. If all that makes sense, if you are following, if you are picking up what I'm putting down, or if it's starting to make sense, let me tell you guys, you already have a huge advantage over most of your competitors on test day. I've been teaching the MCAT for a very long time, almost, gosh, well, 8 years now. This is one of the most common misconceptions. It's one of the most challenging topic areas. And what's great about the MCAT is if it's hard for you and it's hard for everybody else, you don't have to be a pro at acid-base chemistry. You just have to be better than the competition, right? It's like that joke about running from a bear. You don't have to be faster than the bear, just faster than the other people running from the bear. Same idea here, and this is one of the ways that we get faster than the other people running, right? By taking weak areas and turning them into things that we're comfortable with first, and then strengths later on. Thanks, Kenzie. Thanks, Kenzie. I have always been told I look young, and I'm old enough now. It's really paying off. All right, you guys ready for an MCAT style practice question? You want to see this, what this might look like on the actual exam? I bet I know the answer to that. Why did I even ask? Of course you are. Let's take a look at an MCAT style practice question. Allie, if we can get an ABCD poll up so that everybody can play along at home, let's go ahead and switch over to our first practice question of the day. Let's do this in Darcy, it's always so hard to tell on the internet if that was like a sure or like a sure. I bet it was the first one. Those cool sunglasses tell me that you're probably pretty excited. Let's dig into this one. Question number 1. The ionization constant of H2S is A, near 0, B, much less than 1, C, about 1, or D, much less than 1. Boy, oh boy. This is the MCAT's favorite game, right? This is the MCAT's absolute favorite game, is to take something that is pretty hard, acid-base chemistry, and make it even harder by not giving it to you in English, right? By kind of translating it into their own terminology. And the first thing that we can do to help us with a question like this is to translate it back into our own words, right? So first of all, the ionization constant of H2S, what we're really talking about here is the K value, Ka, the acid dissociation constant for H2S. And when we look at the answer choices, we now know a little bit more about these answer choices than maybe we would have about a half an hour ago. Let's take a look at C and D. Ka of about 1 or a Ka much more than 1. Let's translate that into our own terms. If I'm an acid and my Ka value is much more than 1, what does that mean? What kind of an acid am I? If I am an acid and my Ka value is much more than 1, what kind of an acid am I? Yeah. Ka value much more than 1, that's a strong acid, right? That's one that nearly completely dissociates, that favors products at equilibrium. Exactly. So when we take a look at letter D, this is AKA a strong acid, right? AKA a strong acid. Or if you take a look at letter C, about 1, this is AKA pretty much a strong acid. One that's right there on the bubble, that is nearly a strong acid, or just thereabouts. Then we take a look at A and B. And when I first saw this question, my reaction was, what is the difference between A and B? Near 0 or much less than 1? And I realized, again, this is the MCAT being coy, right? This is the MCAT doing its MCAT thing. What they are really talking about here, near 0, they mean less than 10 to the minus 14, right? An acid or a molecule whose Ka is near 0, that is one that is less reactive than water, right? One that is essentially chemically inert because it is literally, mathematically, in terms of equilibrium constants, is less reactive than water. And that leaves me with letter B, right? If I'm an acid, a molecule whose K value is less than 1 but more than 10 to the minus 14, what kind of molecule am I in that case? For letter B, let's translate this into our own words. What kind of an acid are they asking about in letter B? Good. Yeah, this is one in that intermediate zone, right? This is going to be a weak acid. Already, this question is looking a lot more manageable. And in fact, I'm looking at the results in the poll, and our numbers have just gone up and up and up. We have jumped up 20 percentage points since we started talking about this question. So I can see you guys literally in real time figuring this out. You guys are doing a great job about this. There's one more thing about this question that makes it so MCAT, and you can consult your periodic table if you have to. But take a look right here, H2S. Where do I find sulfur on the periodic table relative to somebody like oxygen? Where do I find sulfur on the periodic table relative to oxygen? Yeah, sulfur is right below oxygen. So what that means is that H2S is going to behave similarly to water, right? Similarly to water. If it's going to be similar to water, then we can rule out C and we can rule out D, because water is not a strong acid or anywhere near a strong acid. And now you guys start to see why letters A and B are so important, right? The MCAT wants you to notice that sulfur is right below oxygen on the periodic table. They do this all the time. They give you atoms that you're not as familiar with, but they expect you to understand periodic trends and how they might influence different properties of molecules. I bet you guys have not studied, most of you have not studied H2S. It doesn't come up commonly, but you have studied water, and this is going to be similar to that. The only thing is, sulfur is one step below oxygen on the periodic table. Sulfur is going to be bigger than oxygen. What that means is that these bonds are going to be weaker than they would be in water. And so what that tells me is that this molecule gives up protons slightly more readily than water, right? It's slightly more acidic than water. With that, you guys make your final selections in the poll, and we will let you guys know the results. Good. Yeah, survey says a molecule that is slightly more acidic than water, that is going to be a weak acid, right? It's in that range between not a strong acid, but more reactive than water. That's what makes something a weak acid, okay? You guys are just crushing this. You're just doing so good. Again, this is one of the hardest topics, and honestly, this is something that a lot of students walk into the MCAT not ever really truly understanding. But to me, it's all about being very clear about our definitions, right? We know exactly what makes an acid strong, weak, or we can say when a molecule isn't even really an acid at all. Cool. Now that we've got our definitions out of the way, let's turn our attention to, I can feel you guys out there groaning. Oh, math. Don't worry. Again, I promised you all that the computations are over for tonight. I'm not here to talk to you about math. I'm here to talk to you about ninja tricks for shortcutting math. And that's what we're going to learn on this slide is there's no better way to put it, a ninja trick for shortcutting the math. What we've got to do first and foremost is talk about what we're going to learn. How to calculate pH, how to calculate pOH, how to calculate pKa, how to calculate pKb, all these different numbers that get kicked around in chemistry all the time. But I want to help you guys out with this, right? First and foremost, because that P, that letter P, shows up almost exclusively in acid-base chemistry, it's easy to forget that it's just a mathematical operator. It's telling me to do something very specific and math-y. Let me ask you guys, when I see P, what is it telling me to do? It's almost like an exponent or a square root sign. It's just telling me to do something different. But specifically, what is P telling me to do? Yeah, it's kind of like right here on screen if you're very observant. I'm going to minus log it, right? I can P any number. I can take the P of the number of people who are chuckling at the term P right now. I could take the P of the total number of people who've come to MCAT Channel Week this week. I could take the P of the number of dollars in my bank account, right? The P of the number of dollars in my bank account would be a very big number, which is not a good thing. It's not a good thing, because let me ask you guys, if the P of the number of dollars in my bank account is very big, what does that tell you about the actual number of dollars in my bank account? If the P of the number of dollars in my bank account is very big, the actual number of dollars in my bank account must be very small. Yeah, poor me. I get paid on Thursday. What are you going to do? It's one day away. That's the minus sign in this relationship, right? What it tells me is that the bigger number inside the log the smaller the actual output, or vice versa. The bigger the number on the left-hand side, the smaller the number on the right-hand side. This is such an easy trap to fall into on test day, because when we're in a hurry and the clock is ticking and they give us a pKa, it's really easy to get that turned around and mistaken for good old-fashioned Ka, okay? Make that mistake. Make it a dozen times. Get questions like this wrong. Just learn from your mistakes, because that's the way that you get better. That said, I want to take a look at a couple of examples here. And again, we're going to call this pseudo math, ninja trick math, right? On the MCAT, I don't want you guys doing lots of hard calculations. So let's take a look at this here. If I have a number 1 times 10 to the minus 1, right? Maybe that's the number of dollars in my bank account, so I have 10 cents in my bank account. Now, maybe that's the proton concentration or something like that. We want to p that value. And actually, let me ask you guys, there's no math required for a number like this. What is the minus log of 10 to the minus 1? That's what I'm going for, Allie. You did crimp your hair today, so we are right back in middle school. Yeah, I just look at the exponent, right? In fact, that's literally what a logarithm tells me to do. It says take that number that you stuck in the log and look at the exponent, right? The exponent here is minus 1, but the minus signs cancel, so it just gives me good old-fashioned 1. Good old-fashioned 1. Cool, right? Same thing, if I wanted to do 1 times 10 to the 8th, what I'm going to do is I'm going to look at the exponent. The exponent here is 8, but I've got a minus log, so my output ends up being minus 8. Cool. So that's been pretty easy so far. But the MCAT, of course, they're going to do this. They're going to give you numbers like the one shown on screen. 6.4 times 10 to the minus 3, and it's calculator time, right? We don't get calculators on this test. But gang, what is the number going, if I take the minus log of this number, what is it nearly going to equal? What is it, like, what number is it going to be around? What number is it going to be near? Same drill, right? Same drill. We just look at the exponent, right? It's going to be nearly 3. It's going to be around 3. 3-ish. Yeah. And Jeremiah, I want you to be careful, dude, right? You're on the right track. It's going to be near 3. And same thing, Samuel. Let's think about this, right? But what we're seeing is a number that is slightly bigger. So the output is going to be slightly bigger, or slightly smaller, right? The input is a little bit bigger than 1 times 10 to the minus 3, so the output is going to be a little bit smaller than we would predict. In fact, we can do a little bit better than that, right? This is not calculator time necessarily. What we can do is we can write any number. We can write any number as I call it the mantissa, the number out front. You might have been taught it's called the coefficient, or you might have just blocked this from your memory. But I'm going to call it the mantissa. I'm from Indiana, and that's what we learn it as. Because any number in scientific notation can be written as the mantissa times 10 to the minus exponent. So what we're going to do is we're going to set up this formula. We're going to do exponent minus 1, right? Because we're expecting that the output is slightly smaller than we might predict. Point 10 minus mantissa, right? I'll do one first and show you guys what I mean by this, right? For this number, we're going to do exponent, which is 3, minus 1, point 10 minus the mantissa, which we'll just round to 6. 3 minus 1, point 10 minus 6. And our exponent then is, our output that is going to be 2.4. 2.4. Notice, it's near 3, right? But it's a little bit less than 3. How many of you guys out there feel like Neo in the Matrix right now? Just like, wow, what? I can stop bullets with my mind? Yeah. Good stuff. And by the way, I should mention, this is an approximation, right? This is an approximation. So if you plug in your calculator, you'll get a slightly different number, right? That's probably why nobody ever taught you this before. But on the MCAT, we're not worried about exact, like sig fig accurate numbers. We're worried about approximations. Cool. Let me give one over to you guys. Let's say that I've got a number 2.1 times 10 to the minus 8, and I want to minus log it. I want to p that number. Do our trick. Do our ninja trick. Remember, exponent minus 1, point 10 minus mantissa, and you guys tell me what the output is going to be. You guys tell me what the output of that is going to be. Brilliant. Excellent. Yes. Rhea, Ashka, Raghav, exactly. Notice, it's near 8, right? It's near the exponent, but it's a little bit smaller than the exponent. So if you give me this number on test day, you say take the p of that number, take the minus log of that number, the very first thing I'm going to do is I'm going to look at the answer choices and say, okay, is one of them near 8? Because that's going to be the right answer. But if I have to take it to the next level, right, if I've got to go Neo on this, I'm going to do my ninja trick, 7.8, right? There we go. And we have our output just like magic. Just like magic. Cool. Alrighty, everybody. Let's take a look next at our second learning objective. So that was acid-base strength, and it is a really big deal. It's a really hard topic. Shirley, we can do that trick one more time. Actually, yeah, before we move on, Shirley, I know you're not the only one who wants to see it again. And the cool thing is, gang, with this trick, you can literally just make up your own numbers, plug them in, and then check them against your calculator, right? You don't need me. You don't need me to help you out with this anymore. You guys can go fly free, little birdies. But here, I think this is enough data to remind you guys. I'm just going to make a number up. I'm just going to make one up right now, just for Shirley. I'm having fun with this. Let's do 3 times 10 to the minus 11. Bust it out for me one more time, ladies and gentlemen. What would I get when I p that number? (6.2 times 10 to the 23rd). You could do it with 6.2 times 10 to the 23rd, Samuel. It would work. You'd have to be careful with your sign conventions for the exponents. But yeah, when I take a look at this number, the exponent is 10, so 10 or is 11, so 11 minus 1 is 10. 0.7. Nice job, everybody. Yeah. Patrick, buddy, again, you got a good qualitative trick, right? If my exponent is 11, my answer should be a little bit less than 11, right? So not a little bit more. And if you keep these both the qualitative and the kind of math trick in mind, you are going to crush any calculations involving p functions on the MCAT. All right, as much fun as Allie has had making fun of me for my terminology, it's time to deprive her of that small joy and move on to our next learning objective. Calculate gram equivalent weight and normality. These are two topics that are sort of special to acid-base chemistry. They are a little bit lower yield on this exam. But one of the best things that, at least for me on the MCAT channel, that I love teaching is this kind of stuff, right? This stuff that is, you know, it's like the I hope I don't see that kind of stuff. Like, I'll be okay as long as X doesn't pop up. That is my favorite stuff to teach, and that's exactly what we're going to teach right now. This probably will not be on your test. Maybe a 1 in 3 chance it will be, but if it is, we're going to be prepared. We're going to rock it out. right now, right? What, and if this is French so far, we're going to break it down piece by piece. When we talk about gram equivalent weight and normality, what we're really talking about is special ways of measuring concentration for acids and bases. And let me back up to the very beginning of this, right? If I am dealing with an acid, something like H2SO4, let's say, and I'm thinking about acid-base chemistry, and the example is, let me actually write it, H2SO4. What part of H2SO4 is actually the interesting part to me in acid-base chemistry? What part of H2SO4 is actually interesting to me in acid-base chemistry? Yeah, hydrogen, right? I don't actually care about the number of molecules of H2SO4 that I have. What I care about is the number of protons that I'm going to get from H2SO4, that maybe I could get. Maybe if I unleashed an army of bases on this molecule, how many protons could they steal from this molecule, right? So when we think about gram equivalent weight or normality, what these are is a way for correcting for the number of protons, because that's what we actually care about with these molecules. Let me give you an example, right? So this is something that's going to get clearer and clearer the more examples that we do, right? If I have HCl, right, and I have a mole of HCl, that's going to turn to 1 mole of protons. Chemists come up with this sort of fancy, sort of weird word for that. Instead of calling it a mole of protons, they call it an equivalent of protons. But I want you guys to notice here, this literally means that if I stick a mole of HCl in a solution, I would expect 6.02 times 10 to the 23rd protons in solution. That is what 1 equivalent of protons literally is. It's a number, right? But let's think about my buddy H2SO4. If I have 1 mole of H2SO4 in solution, how many moles of protons, aka equivalents of protons, can I get off that guy? 1 mole of H2SO4, how many moles of protons am I going to get? Yeah. 2, right? 2 equivalents. So we say this guy gives me 2 equivalents of protons. And again, when a scientist says equivalent, they literally mean a mole of protons. That's it. That's all they mean. Right on. But this doesn't just work for acids. This also works for bases, right? If we want to think about a base, something like calcium hydroxide, here. Notice that per molecule of calcium 2 hydroxide, I get 2 OHs. So if I have 1 mole of calcium hydroxide in solution, that means I can accept 2 moles of protons. And again, the way science nerds say this, like myself, is I have 2 equivalents of base for 1 mole of calcium hydroxide. But what that really means in English is just that I can accept 2 moles of protons. Let's do one more example of this. I'll make one up for you guys. If I have PO4 3 minus. And let's make this one a little bit harder, not just 1 mole. Let's say that I have, I don't know, 0.2 moles of PO4 3 minus. 0.2 moles of this guy. How many moles total of protons can I accept? Can I bind up with my 0.2 moles of PO4 3 minus? And note the 3 minus is a really big hint on this one. How many total moles of protons can that species accept? And I you know, it's not that I had to work on that nerd voice. It's actually the opposite. I had to work on not sounding like that all the time. Darcy, I love it. Yeah, 0.2 times 3, right? I can accept 0.6 total moles of protons. This guy can bind up 0.6, and again, a scientist would say 0.6 equivalents of protons, but it's just 0.6 moles of protons. 0.6, I'm going to type this, moles of protons accepted, right? That's what an equivalent is. That's what reacting equivalence means. It's nothing fancy. It's nothing to be intimidated by. It's just that in acid-base chemistry, what we really care about is the number of moles of protons that we're donating to solution, or about the number of moles of protons that we are accepting from solution. So let's take this idea and let's apply it to gram equivalent weight. The definition of gram equivalent weight is right here on screen. Gram equivalent, you can see here, G per EQ. That's where we get the name gram equivalent. Now that's still kind of French to me. So let's tie that back to something I guarantee you guys know a lot about, right? Grams per mole, right here. Let me ask you guys, what is grams per mole? What does that mean? Where do we find grams per mole? I love the logic, Emma. I know it takes longer to type, but it's totally worth it. Yeah, this is molecular weight. Molecular mass, right, or atomic mass. Literally, if you go on the periodic table, Ashka, you nailed it, right, Sasha? If I go on the periodic table, that is literally the number that I find right there, right? The atomic mass of those atoms, the number of grams per mole per carbon, or something like that. So what we're talking about, the gram equivalent weight, is very, very similar to our atomic mass, right? It's just atomic mass adjusted for by this conversion factor, because again, when I deal with H2SO4, I don't actually care about the atomic mass of H2SO4. What I care about is the number of protons I'm going to be able to get off of somebody like H2SO4. So let's try this out. Let's play a little game with this, right? First and foremost, we've got NaOH, right? NaOH, we're given the atomic mass, it's 40 grams per mole. Now let me ask you guys, each molecule of NaOH, how many protons can each NaOH accept? Each molecule of NaOH, how many protons can he accept? Or she, I don't know. Yeah, 1, right? It's a 1-to-1 ratio. 1 mole of NaOH molecules is going to accept 1 mole of protons. So this ratio right here, how many moles of the molecule do I have versus how many moles of protons can it accept? That ratio is just going to be 1-to-1. What is brilliant about this is if I have, the nerd term for this is a monovalent base, a base that can only accept 1 proton, its molecular mass is its gram equivalent weight. We don't need to worry about this. If something is a single proton donor, if something is a single proton acceptor, it doesn't actually matter, right? We're going to be just using that 1-to-1 ratio. It's only when we have these divalent acids or bases, bases that can accept 2 protons, or acids that donate 2 protons, that are going to matter. So let's play this same game here. You guys tell me, if I'm a molecule of sodium carbonate, think about this is going to dissociate in solution into carbonate, what the charge would be, and how many protons can I accept? How many protons can I accept if I'm carbonate? Chris, this is going to start getting, if you want to go down that road, this is going to start to get real freaky real quick. If OH minus is a monogamous base, what does that make carbonate? Yeah, we get 2 equivalents. 2 equivalents. So my ratio here is going to be 1 to 2. The way that you want, the way that you can make sure you've got the ratio plugged in correctly is that the moles are going to cancel. Right? 1 mole of carbonate accepts 2 moles of protons. I make sure that my units cancel, and that gives me the gram equivalent weight. What this says in English, and I'll write this down because it's sort of a wonky definition, but what this says is 53 grams of Na2CO3 binds 1 mole of protons, right? A half a mole of sodium carbonate binds up 1 mole of protons, right? 53 grams is a half a mole of this stuff. That's going to bind 1 mole of protons. it's really not so intimidating when you take these equations and kind of pop under the hood, when you look at what they're useful for. Ashka, when do you use gram equivalent weights? When the MCAT asks you to provide an answer in gram equivalent weights. Another time that you would use gram equivalent weights is if you are in, so a practical application is if you're in chem lab and you need to go to the literal jar of sodium carbonate and weigh out enough sodium carbonate to react with 1 mole of protons, you would weigh out, in this case, 53 grams of the sodium carbonate, and that would be enough sodium carbonate to react with 1 mole of acid. Maybe you're making a buffer solution or something like that, and so you know, okay, I need 53 grams of this stuff that'll react with 1 mole of protons. It's a really good question. It's a really good question. Sorry for the MCAT joke. I can't really help myself. Cool. Let's take a look at normality. Oops, I did not mean to delete all that stuff. Let's take a look at normality. Here is again the definition of normality. We've already seen with gram equivalent weights that we can pop under the hood. Things are not going to be too bad for us once we break this down, because when I look at the definition of normality, I look right here first and foremost, moles per liter. And again, ladies and gentlemen, fellow chemists and future doctors, what is moles per liter? What is moles per liter? Jillian, the secret is you did all of this already, right? You already took physics and you already took chemistry. Yeah, molarity, right? This is just good old-fashioned molarity. We all know and love molarity. It's my favorite kind of concentration. Absolutely. Big M, Sasha. Yeah, so we're just going to take something that I already know a lot about, that I'm already used to working with from OChem Lab, and we're going to modify it with this conversion factor. Now, my question, this is really important for you guys to notice, right? Here's my conversion factor. What do you notice about this version of the conversion factor compared to the last version of conversion factor? I just want to make sure that you guys are making this connection. What is different this time around? Yeah, it's flipped. It's flipped. It's flipped. It's the inverse, right? Again, don't let this throw you off. Just start with normality and make sure that your units cancel, right? Just make sure that your units cancel and you guys are going to be good to go with this. We'll do another quick example. Another quick example of this. We've got H2SO4. Notice, divalent, right? It's got those 2 protons, and we have a normality of 10 to the minus 1. So what we're going to want to do is we're going to want to think about how many protons are going to be donated by this. And let me give you guys a hint. 2 protons per mole, 2 moles of protons per mole of molecules, right? You guys tell me then, what is going to be the normality of this, what's going to be the normality of this molecule? While you guys are telling me that, let me comment on the Nick Miller thing. I have been told that before. The other one that I also get is Charlie Kelly from It's Always Sunny in Philadelphia. And I can always tell if the group is a good group, or if they like me or if they don't like me based on whether they're like, you sound like lovable Nick Miller, or you sound like despicable Charlie Kelly. So thank you guys. I'll take it as a compliment. I don't know. It's good to stand out, I guess. Totally. Back to our question, the normality. Not seen it come through yet. Charlie is a treasure. Yeah, so literally all we're doing here, gang, is we are taking the molarity and just multiplying it by 2, right? And what this means in English is if I have 10 to the minus 1 molecules of H2SO4, 10 to the minus 1 moles of H2SO4 molecule, then I have 2 times 10 to the minus 1 protons, right? Because it's actually the protons that are what I care about, right? 2 for 1. 2 for 1. You just multiply it by 2, and that gets you to normality. Great. Let's do a quick application of this. We'll do one more MCAT style question, and then Allie is telling me, unfortunately, my time with you guys is coming to an end, which I'm super happy we get to spend this time together. So let's go ahead and give this one a whirl. This question gives us data about phosphoric acid and about hydrochloric acid. And it tells us that we have a certain amount of water. We're asked which one is going to have the greater concentration of protons. First and foremost, one of the great things about the MCAT, take a look at our trend here in the answer choices. We are never filling in the blank. We are only ever picking 1 from 4. And we've got what I like to call the 2x2 answer matrix, right? It's either hydrochloric acid in A and B or phosphoric acid in C and D, and it's either because of molarity in A and C or normality in B and D, right? This is actually 2 simpler questions that we can go ahead and answer, and the final answer will be kind of the combination of those things. Now, if we take a look at the data that we're given, notice I have 36 grams of hydrochloric acid, and the molecular weight of hydrochloric acid is 36 grams per mole. So pretty straightforward here. I can see I've got 1 mole of hydrochloric acid. But as far as my top answer choice goes here, my top piece of datum here, 49 grams of phosphoric acid at a weight of 98 grams per mole. So what we're saying here is I've got 1 mole of HCl versus only a half a mole of phosphoric acid. The thing about phosphoric acid, though, is that it's triprotic, H3PO4. Right? So when we figure out the total number of protons that we're going to get from these molecules, with HCl, it's just a 1-to-1 conversion, right? 1 mole of protons. But when we think about H3PO4, let me ask you guys, how many total protons can that guy donate to solution? If I've got a half a mole of a triprotic acid, how many total protons is that guy going to be giving me into solution? Yeah, 3 equivalents, exactly. Now keep in mind, gang, the equivalents are the number of protons I get off of each of these guys. So I'm going to have to multiply that by a half, but I get 1.5 moles of protons in solution. So even though I had a fewer number of H3PO4 molecules, I'm going to end up with more moles of protons, and in acid-base chemistry, it is the protons that I care about. Lastly, when we take a look at the answer choices C versus D here, we want to think about the kind of concentration. We want to think about the kind of concentration that actually accounts for the number of protons. And if I'm looking in the poll here, most of you guys are zeroing in on letter D. Normality is the concentration that cares about protons, not molecules overall. We did have a question about why it's a half a mole. That was this data point at the very top. I have 49 grams of phosphoric acid, and the molecular weight is 98 grams per mole. So that's a half a mole of phosphoric acid. But I'm loving it, guys. I'll tell you, actually, when we opened the poll, 75% of you initially chose letter A. It ended up getting over to 86% of you on letter D by the time we got done talking about this. So let me actually wrap this up with you guys. I'm going to hand it back to Allie. But before we go, how do you guys feel about acid-base chemistry now? Better, I hope. Was this fun? Did you guys have a good time? Nice. Cool. Nice, Milanis. Guys, I'm so happy to have had the opportunity to teach with you guys tonight. This is what I do most every night, but usually with our students, and it's been a real honor. I mean, I know you guys are maybe just studying for the MCAT, so you didn't have to come tonight, and it really means a lot to me that you guys did. You guys are just starting out on your journey, most of you guys. So, you know, it's a long road, and keep working hard. We all have been there. All of us behind the curtain, so to speak. We all have been in your shoes once upon a time. I was brand new to this, and my head was spinning too, okay? You guys can get there. It's gonna be hard work, but you guys, I know, are hard workers, okay? That's what I want to leave you with. I'm going to turn things back over to Allie. I'm going to be off camera if you guys want to ask any questions or anything like that. You guys have just been such a fun group, and thank you so much. Bye, everyone. Bye. I miss you already.
Oh my gosh. Oh my God. Was he not so good? Didn't I tell you? Didn't I tell you? That he was going to be, you know how I know for a certain fact, I love every one of you right now. I just love y'all so much. I feel like I finally found my people. But you know, I got to get on to my topic. Y'all asked me many times this week, when is the lesson when we're going to talk about MCAT scheduling on a calendar? When is the lesson? Here it is. Here it is. Hold on. Let me go back to my classroom. Let me go back to my classroom. Hold on. Here it goes. All right, here we are. This is a calendar, but you will notice to the right that there is a flaw. Please let me know. Take a few seconds, maybe about 9, and tell me what is wrong with this calendar. As your coach, I'm not happy with you right now. You made this calendar and I'm mad at you. I'm going to help you fix it. You're lucky to have a coach today because this calendar's all wrong. What's wrong with it? What's wrong with it? I know you know. I know you know. Oh, I just got frozen in the weirdest face. Goodness. It has no breaks. How did you not know that? There's no breaks in this calendar. Thank you. There you go. All right. I didn't wait long enough. I got ahead of myself. Exactly. There's no breaks. You have to take time off. Your brain is part of your body. Oh, Emma, you're so right. So we learned that yesterday, that in order to get things into our long-term memory for retention and for ease of use whenever we want it, the most efficient way to go about that is studying many things in different ways, right? Not just sticking to one type of thing. Now, okay, you guys are good. Yes, you need a break. Of course you need a break. Everybody needs a break. Give me a break. All right, here we go. Talk to me about my conclusions. Look at this. Do you want to be the green line or do you want to be the blue line? So they did a study, and what they found, the proverbial day, they kind of start off feeling like you're doing better than other people. But listen, y'all, check on that. I know y'all know there's got to be some of y'all that have been serious. Leg day is not the best day. I'm into arm day. I'm trying to get them Obama arms. I'm working on that. So you want to do wakeful resting. You got to take breaks. It's going to improve your recall in short and long term. And you know how I love long term. We talked about that yesterday. All right, we're going to go for another flaw. Here we go. Here we go. Tell me what's wrong with it. What's wrong with it? Tell me what's wrong with it. Listen, y'all, it's on the top of the slide. I mean, it's there. You don't have to think too hard about it. All right, so we got no specificity here. Do something empty. Sometime in these blocks, you're just going to get really kind of, oops, where did I go? Click the wrong button. You got to make it more specific. I think as a coach too, maintain it, right, for your long-term memory. We need you. Neither am I, Crystal, but you know what? We got to build our endurance. So we want to start making longer and longer study breaks if we can. Yes, Mike, be specific. Be specific. I totally forgot my original train of thought. You guys are so great. You guys are so great. Let's keep it moving. Look at this one. What's wrong with this one? If y'all don't start speeding up with which one is wrong, I worry about all of you for the MCAT because it is written there on the top of the slide. It is not realistic, of course. It says it is not realistic. Because of course I can do 4 hours of this stuff every single where, and of course I can go out to my MCAT classes at Kaplan, do all of this because I'm going to rest all day long on Monday through Friday. How many of y'all have Monday through Friday days off to just like hang out? You just hang out. You're just resting the whole time. You're just resting. Okay, hold on. I'm going to turn off my camera because I'm having some issues. I'm going to turn it off. I'm going to turn it back on. Hopefully that fixes it. But I know that you guys don't have time because we talked about it before. And aside from leg day, who is shadowing? Who is going to classes? Who has volunteer work? Who is doing every single thing on top of trying to work on the MCAT? I know you are. Adrian, you're funny. So in order to be realistic, you got to think about all of the
Hey everybody, I told you I wasn't going too far. This is your buddy Tyler, and it looks like Allie is refreshing the
things that you're doing in your life, not just the MCAT. This is like me. I can't do any of this. And so, and remember.
So in the meantime, I'm going to talk to you guys about calendar stuff because it's one of my favorites. Where Allie was kind of getting around to the there we go, getting around to the actual like final schedule that we would want to be looking at. Right? So here we have someone who has got they've got a ton of different responsibilities. And what I would usually recommend to a student is that we pre-program in those responsibilities first, right? So Allie was talking about what if, you know, how many of you guys are in college classes, you're in your MCAT class, you're volunteering at the community center, you've got studying for exams, you've got doctor's appointments, right? What I would recommend to any student is to start your study calendar by putting that stuff in first, because you know you got to do it, right? You can't get out of it. But then after you've got all of your personal commitments or all your professional commitments in, next put in your professional commitments. Guys and gals, I have studied for the MCAT. The truth is I actually studied for it twice, right? Once before I took a Kaplan class, and then again after I took my Kaplan class. You are going to need time to yourself, right? You are going to need a break. You are going to need, it's probably not the right time for beach time with Marco, Sam, and Fatima, but, you know, maybe if you want to go freeze your buns off on the beach right now, you're going to want to have lunch with your friend Sarah. You are certainly going to want to keep up your gym routine. I'm actually a bit of a night gym person, but the same diff, right? You want to keep date nights with Sam. Ooh. Friday night fun time, I guess, right? You definitely want to make room for this stuff because your prep is way too long and way too hard to be slacking on that me time. But this is the really important part, gang, right? Once you've got your personal commitments on the page and you've got your professional commitments on the page, once you've got your work times and your rest times all blocked off, what is all of this other extra time, all of these blocks of time that aren't accounted for, what does all of this represent? Yeah, this is pure sleep time. Eating time. You're going to want some sleep and some eating in there too. But outside the sleep and the eating, that's all pure MCAT study time. Exactly, everybody, right? So what we've done is we started with a bunch of just indiscrete blocks of random study time. You guys know what blocks of random study time look like, right? You go to the library, you spend half the time taking laps, saying hi to your friends, and the other half of the time on social media. And now where we're ending with is this very discrete schedule where we have blocked off time for our professional commitments. We have blocked off time for mom and dad, for our friends and family. And we've blocked off time for our MCAT class. What is left with this is pure study time divided up into small 1-hour blocks that have a discrete purpose and are very manageable. This is kind of like the reverse building study plan method. Most students start by writing down their MCAT study time, and then they find that their real life is constantly cutting into their MCAT study time. What I recommend to you guys is to start with the opposite. Start with everything else in your life. And then you know what? If studying for anatomy ends up not taking as much time as you thought it would, suddenly MCAT time starts eating into your real life, right? Suddenly you've got a block of time there that is going to work for you guys. It looks like Allie's dancing on camera now. So I think we're going to give it back over to her and she's going to take it home, but I'll still be here. So thanks again, everybody.
Of course, I didn't turn my microphone on. Like, can I have more technical issues tonight? Isn't it great? Can I tell y'all why he's so great at teaching this particular calendar? It's because he made it. It's ages thing. He sounds like they can't go wrong with Tyler. You should all join his MCAT class. You know, he is a teacher here at Kaplan, so you can do that. Listen, y'all, we did it again. We pushed it right to the minute. Y'all know that I love it. I don't know how much we're going to get to today. Tomorrow is molecular genetics. I am. Oh, is that what it sounded like, Adrian? I don't know what happened. I did have. I'm going to Send out tonight. Did you guys email my poll? Let me open this poll one more time just to make sure everybody gets their email in there. Guys, put in your homework today.
I think Allie is kind of skipping out everybody.
Y'all you guys know that I'm helping y'all to read with and choose my
what we wanted to say as a wrapping up message. Thank you guys so much for coming out tonight. Tomorrow night we're doing some more molecular genetics. In the meantime, and we want to see you back here again. So definitely give us your email. Let's get registered to see you guys again tonight. If you have any questions about what you saw tonight, you want to get in touch with us. We are all here off camera waiting to chat with you guys. And I can definitely take any questions for you guys while I am on microphone as well. What questions can we help you guys with? Hey, thank you, Samuel. It really is a great job. I got to teach organic chemistry last night and regular chemistry tonight, and I'm teaching math tomorrow night. All right, everybody. I'm going to jump off camera then and microphone and let the off camera. Oh, Allie, what's wrong with your computer? You know, I always assume it's like Princeton Review. They've just come to sabotage us. They've got their spies everywhere. That's probably not the case. I'm probably going to get sued now. Oh, Hadil, would we ever have to balance on the MCAT? So one, you've got to balance your time on the MCAT because the clock is ticking at every moment. But outside of the jokes, yes, there are questions about balancing equations. One of the most common places that you would see that is if you had to balance an equation, a chemical equation, as part of a bigger or harder question. So absolutely. Yeah. Hey, thank you, Gagan. Hannah, thank you so much. I wish I was coming back tomorrow night for more. You guys have been a blast.